The electron, a subatomic particle carrying a negative charge. All elements possess an intrinsic number of electrons, and these electrons are what define their chemical reactivity. And so, to manipulate the flow of electrons in chemical compounds is to control the ways in which they behave, the ways in which they react. The chemist is a conductor, presiding over the magnificent orchestra of electronic motion. I am such a chemist. And I study the flow of electrons within and between molecules. These are important processes. You see, I can get chemical reactions to occur by carefully managing the inventory of electrons available to a given system. Countless products that are ubiquitous in our daily lives, such as steel, textiles, plastics, fragrances, flavorings, medications, and more, are made in chemical processes that involve the flow of electrons from one species to another. Take a look at the molecules shown here on the screen. These are actually medications used to treat conditions ranging from HIV to arthritis to mental illness. What do they have in common? The trifluoromethyl group, a carbon atom surrounded by 3 fluorine atoms. This group is extremely prevalent in modern-day pharmaceuticals, but it can be a challenge to make. Fluorine is one of the hardest elements in the entire universe to remove electrons from. Its unwillingness to part ways with its electrons limits the number of ways we chemists can engage fluorine in fluorinated compounds in chemical reactivity. Take, for example, trifluoroacetate, or TFA for short. This cheap and widely available compound would be an ideal trifluoromethyl source. But to use it as such, we need to remove an electron from it, something TFA will just not do willingly. Let's imagine for a second that we could remove an electron from TFA, however. In doing so, we would destabilize the molecule, causing it to rapidly fragment into carbon dioxide and a reactive trifluoromethyl group, which we can then harness for pharmaceutical synthesis. But alas, removing electrons from TFA's vault is just too hard. And so we often derive the trifluoromethyl group from other synthetic sources that are easier to use. However, they tend to be a lot more expensive. Naturally, as a first-year graduate student, I was obsessed with achieving an unnatural flow of electrons, that which goes against the natural dogma, like water flowing up instead of down. And so I was motivated to take on this challenge, the challenge of how can we remove electrons from TFA itself? To do so would be no easy task. When it comes to TFA, you can't just walk through the front door and expect to take its electrons. No. I would need the ultimate bank robber, a compound that wants electrons so badly, it will take them from anyone, anywhere, anytime. The compound I devised to undertake this task is based upon silver, but not any type of silver you have ever seen or encountered before. An exotic form of silver, whose very existence is the product of the unnatural movement of electrons. The silver metal that we all know and love is a stable form of silver, possessing all of its electrons. The chemical symbol for silver, Ag, is derived from the Latin word argentum, and we've been dealing in its currencies and jewelries for centuries. I can actually take an electron away from silver quite easily. In doing so, I make the silver 1 ion, which is stable. Many compounds containing silver 1 are known, compounds you may have even encountered before in your daily lives. But to take a second electron away from silver, now that is unnatural. The silver 2 ion that results is a beast with an insatiable hunger to reclaim its missing electron. A thief, an electron kleptomaniac, if you will. It will stop at nothing to reclaim its missing piece. And so it was the perfect tool for me. A tool to achieve a flow of electrons away from TFA. But to wield this tool would be no easy task, as that would mean that I would have to tame silver 2. And at the outset of my PhD, very few silver 2 compounds had ever been made before. But in this absence of knowledge, in this lack of precedence, I saw opportunity. And I seized it in the lab by devising a new synthetic strategy towards isolating large quantities of silver 2 compounds. I began by dissolving organic supporting molecules into a superacidic solution, followed by the addition of a special silver ingredient. The red color that forms is due to the generation of this compound, shown here, which I could isolate as a gorgeous red solid and hold in the palm of my gloved hand. This compound promised to usher in a new era of silver chemistry. When this compound was mixed with solutions containing TFA, a new compound was formed, one in which TFA was bonded directly to the silver 2 center. This molecule is poised for reaction, a ticking time bomb. It just needs a little push, a little energy to get things going. And what better energy than that which sustains all life on Earth, that which is illuminating this very room right now? Light. Light consists of packets of energy called photons, and silver 2 can harness this photonic energy to rip an electron away from TFA. I'll show you. When LED lights are trained onto the molecule, the incident light is absorbed, and the molecule enters an excited state. Within this excited state, an electron is transferred from TFA to silver 2, resulting in a stable silver 1 ion and breaking the bond between the two. The destabilized TFA fragment then breaks, as we've seen before, yielding trifluoromethyl groups that can then be harnessed for medicinally relevant synthesis. Even better, I can reuse the silver molecule. By hooking the system up to a voltage no greater than that supplied by a AAA battery, I can turn the silver 1 photoproduct back into silver 2. And I can use it over and over and over again to generate tens of trifluoromethyl groups per silver molecule. And so in my reactions, silver makes up less than 1% of the overall reaction mixture by mass. Science is truly a team sport, and I would like to thank those who embarked on this journey with me from the Nocera lab, because without them, none of this would have been possible. I would also like to acknowledge generous support from the National Science Foundation, the National Institutes of Health, and the Department of Energy. But for now, I want to leave you all with a tantalizing question, one that we have only barely started to scratch the surface of in the Nocera lab. If silver 2 can remove electrons from TFA with only the aid of visible light, are any electrons truly safe from silver 2's grasp? Thank you.